So, hello everyone, and welcome to our live webinar series organized by Computing Analytical Method Subcommittees, or CAMS. Just a brief introduction about our subcommittee, which is part of Analytical Methods for Power System Committee, which is part of IEEE Power Energy Society. Our mission is to serve as a bridge between the technical areas of sophisticated analytical modeling algorithm and state-of-the-art information technologies, especially the integration and computing methodologies. Our activities include 4 working groups, 1 task force, and 1 standard. And we welcome new members who are interested in the analytical algorithms, modeling, computing application, and system integration to join. You can find more information on our website down here, including the recording of this presentation. And it is my great pleasure to introduce our speaker, Dr. Mihai Anitescu. Dr. Mihai Anitescu is a senior computational mathematician in the Mathematics and Computer Science Division in Argonne National Laboratory and a professor in the Department of Statistics at the University of Chicago. He obtained his engineering diploma from the Polytechnical University of Bucharest and his PhD in Applied Mathematical and Computational Sciences from the University of Iowa. He specializes in the areas of numerical optimization, computational science, numerical analysis, and uncertainty quantification. Dr. Anitescu is a fellow of the Society of Industrial and Applied Mathematics, CIM, and he is on the editorial board at the CIM Journal on Optimization Methods and Software. Today, he is going to present us a kinetic Monte Carlo approach for characterizing the distribution of cascading power network failures. Please welcome our speaker. So the floor is open, Dr. Anitescu, you can start.
Okay, let me share my screen now. Okay, this is a screen 2 is what I want to share. You guys are seeing my slides?
Yes.
Okay, so you see the full version, the presenter version, right?
Yes,
the full screen version. Okay, good, great. Okay, well, thank you very much for the invitation, very much for the warm introduction. It's good to see sort of people that are friends, and sort of so I was actually kind of happy when I was invited to speak to this committee, because of course a lot of the stuff, and I'm even happier to see that of course you guys take cascades simulation as a very important part of your mission, because of course that is sort of what the talk today is going to be. It's going to be about kinetic Monte Carlo approach for cascade failure simulation. So you know, a bit of background, maybe sort of okay, well, hopefully I'm not, you know, this is not stuck. Okay, interesting. Okay, it works. So of course, cascade simulations are difficult for a number of reasons. Of course, they're very important. They're critical for the safe planning and operation of the grid. Of course, the growing complexity of the grid rendered the challenge of this problem even more pronounced. And actually, some of the people have tried to do good models for a while, but some of the challenges, of course, is the fact that the component outages do not necessarily propagate locally along the grid topology in a cascade, right? And so here's an example of the event sequence of the of WEC from July 2nd and 3rd of 1996, where you see that sort of that the first 3 failures actually occur somewhere in the middle of the country, but then failure 4 occurs somewhere in the northwest, same not far from failure, you know, then failure 5 again in the middle of the country, then failure 6 sort of somewhere in not quite northwest but close to it, then failure 7, then failure 9 all the way to California, right? So certainly if one were to come up with a way to simulate cascades, you know, the natural way to think about is to think about it like dominoes, but in reality they're not dominoes because they don't propagate locally. Of course, the cascades are a lot more complicated than that. So that is actually part of the challenges. It's actually kind of difficult to think about how to come up with an empirical model of cascades, given the fact that there's no sort of simple way to think about how such, you know, remote events would actually propagate, really. And it requires solving complex interaction between components, grid dynamics, and AC power flow as well as, of course, one of the questions that people ask, because this is a AI intensive kind of period in our research and development. Sometimes, can't you just doing data driven? And the reality, we have so little cascade data, and given the complexity, system is actually hopeless to come up with because there's such rare events, it's hopeless to imagine that you're going to be able to do this from data only. So clearly, you must come up with a system modeling and simulation of some kind, which is maybe informed by the data, but you cannot do it based on data only. So these are some of the challenges, really. So our goal was actually to come up with a framework where the cascades are predictive. And of course, this is a very lofty goal, and it's in some sense impossible. But remember, I'm trying to come up with the framework where cascades exist and are predictive and have some resemblance to reality, and not necessarily to claim that I can account for all possible sources of failure, which of course it's impossible. I should say I certainly do not have the data for that, right? So the moment the endeavor is primarily mathematical, but nevertheless, I hope that I will convince you that it has at least some bearing on reality. So our objective is to construct analytic trackable models for probabilities of individual component failures, accounting for the grid dynamics and AC power flow, as well as the load and duration fluctuation, then to aggregate these failure models based on the individual probabilities, which is where the kinetic Monte Carlo tree is going to come in, and then finally to use that in planning and operations, right? So this would be the objective. Of course, this is a research project. We're not all the way there. We've done quite a bit of one, some of two, and a little bit of three. But I will certainly present, sort of where we are with respect to all three of them. So the mathematical underpinning, the space where these things are in. So what we're going to do is that we're going to take the dynamical equations of the grid and transform them into stochastic dynamical equation to account for the noise on the grid, for the fluctuation. And then we're going to use large deviation theory to approximate the calculation of transitions in a tractable manner. So that would be, so that is from 10,000 feet what's going to happen mathematically. We're going to put down a stochastic differential equation, and then we're going to approximate this transition rate, the failure rates, based on large deviation theory. So that's what's going to occur here. So the outline is roughly like this, which is that we're going to start with the lossless transmission model. So that's the first we applied to, and actually the model is not ours. It's due to Chris DeMarco from the University of Wisconsin. And then we're going to explain how the lossy transmission model will change the calculation. And then finally, we'll talk a little bit about the cascades prevention. Okay, so of course, the power transmission network model, we abstract it as a undirected graph with nodes and edges, B and E, where the nodes are generation, load, or slack. And we assume that we use the swing equations to model generation synchronization. We're going to use the lossless AC power flow equations, so that's going to be that's going to have a bit of a caveat, as well as we're going to have a frequency dependent active load. And just for recollection, because we're going to modify a bit the equation, let me explain how we do that. And actually, sort of even here, I must say that this is work, and I should have started with that, and it was on my first slide, but I was not courteous enough to introduce it. This is work which required the input from many people, like 6 people. There's 2 colleagues of mine at Pacific Northwest National Laboratory in the math side of things, which is Panos Tinis and David Barjasolano, and I work with 3 very talented junior scientists at Argonne, Jake Roth and Rusu Brahmaniam, and finally there's yours truly who's guiding it, and Albert Lamb, and then there's myself. So actually, this is input from many people. So some of the slides, of course, are not derived by me, so I may not be able to answer all the questions, but I'll do my best to present what I understand. So then, so the IC power flow equations, then of course we have the active power flowing into a node, and under the assumption, of course, we have lossless, we have only Bij. Then we have the reactive power flowing into a node, which are familiar equations. And then we're going to use the swing equation for the lossless network, which is the generation swing equation, both in frequency and angle. And then finally, we're the load model is going to be, it's actually going to assume that there's a prescribed reactive power demand, but for the active power, you do have a form of fluctuation, which you do have a frequency-dependent load, as you see here, which is characterized by a damping factor DI, right? And this is data that we do have. This is a fairly classical model so far. So when you put it all together, you get, of course, a differential algebraic equation, which looks like this, right? Theta dot is fundamentally omega I. Then omega I dot comes from the dynamics of the machine. Then you get the theta I dot from the frequency-dependent portion of the load that you see here, and then you have the reactive power balance of the load. So this is sort of almost classical string equation, right? So that's that. So now we will. It's difficult to apply our theory to. It's a bit difficult to apply the theory to differential algebraic equation, though we're trying to do that at the moment. So the way, and this was actually Chris DeMarco's idea, everything I'm sharing here originates with Chris DeMarco. This is not our work, this is his model. So the idea that we're gonna modify the last equation, which is an algebraic equation, we're gonna turn it into a dynamic one and allow it to depend on, and actually have it guide the dynamic of the voltage, right? So this is how we're gonna do it. We're gonna introduce V to the reactive power balance, right? So instead of writing Qi minus Gi equals 0, we're gonna multiply with the diagonal of V. So it's gonna be V inverse times Qi minus Gi, and it should be Vi. And then we're gonna introduce a singularly perturbed dynamics for V based on characteristic parameters dV. So we're gonna get dVV dot is V inverse Qi minus Gi. So when you reach balance, of course, you have Qi is equals Gi, right? So this is just so in his work, Professor DeMarco has shown that this is a good approximation of the dynamics for the fluctuation in the network. So here's why all this, and actually here's the really important part, actually, structurally speaking. So the really important part is that when you put it all together, you obtain the following dynamics. You get omega dot and theta dot, which is something you had before, as long as you assume the frequency-dependent load. So this is not an approximation, but the last equation is indeed the result of the singular perturbation. And the important part is that the dynamics of omega, theta, and V have this very interesting structure with respect to the right-hand side. It's a matrix whose structure you see here times the gradient of a function, which I'll define later. So this is so all this was done so the function can be, so the dynamics can be made to depend on the gradient of a function, which is going to be extremely important for the analysis. Okay, so then this is the definition of the two matrices in terms of the generation indices and the load indices. It would take a while to parse this model, but the important part here is that H, it's what's going to be called here an energy function. And it looks like this. It contains a term of the energy in terms of the frequency at the generator and slack buses, and it's defined by the inertia. Then it contains the terms in voltages, which is defined by the admittances of the lines. And then you have the terms which are defined by the load. So the interesting, right? So the interesting, the interesting part here is that the dynamics can be made to be dependent on the gradient of this function. Now, for people who know this is not exactly a Hamiltonian system, right? So in a Hamiltonian system, you do have x dot equals exactly the gradient. Actually, this is not exactly a Hamiltonian system because you do have damping. But the important part is that the system has a very friendly structure for the analysis. So you can actually write it. So at the end of the day, you can abstract it as x dot equals G minus S times the gradient of this energy function, where J here is Q-symmetric and S is positive semi-definite. And this makes a huge simplification in the calculations we're going to do, as I will explain later. Right, so this is actually, and all the way up to here was actually the work from Chris DeMarco. This is not our derivation, it's Chris DeMarco's derivation. Okay, so now this would be the dynamics of the network with this singular term added to the loads, which derives the voltage at the load buses, right, which drives the voltage at the load buses. So at this stage, which is abstract enough that it actually can fit nicely on a slide, we're actually going to perturb the system by modeling the noise to the system in the following way. We're actually going to assume that the dynamics is actually just the drift part of a stochastic differential equation, which looks like the one I'm pointing here, right? So you get the dx, it's the drift times dt, where the drift is the same as the right-hand side on the classical dynamic equation, plus some scaled version of a Wiener process, right? Which is sort of the most classical way to introduce infinitesimal time noise, right? So this is actually how it's going to look like. So this will be our foundation, right? So at this stage, we assume that this is the truth, right? We assume that this truly describes the dynamic of the system. And from this stage, we're going to wonder the following, right? So this is going to be our mathematical expression for the dynamics of the network, or the stochastic dynamics of the network. And now we're going to start to model line failures. How do we do that? As follows, right? So we will assume that each line has a failure condition on energy. So the idea is that as long as the total energy is underneath some level theta max, the line still operates. But as soon as you encounter theta max, the line fails, and you might account for the fact that you take it off of service, right? So then in this framework, if you accept that this is a good model for line failure, then the problem becomes what in stochastic analysis is called an exit time problem. So we're gonna declare that we obtain a failure if the dynamics exceed the Bayesian of attraction from x bar, which is the original stable point, and has an excursion all the way to x star, which is a point at which you actually trigger the failure condition. So then if we accept this mathematical abstraction, then the problem becomes the problem of estimating the first exit time, as is called in stochastic equation, which is the infimum among all times of all the circumstances when the trajectory reaches the boundary. So let me make another observation about the energy function. You can actually show that any solution to grad h equals 0, it's a solution of the power flow equation, right? So to some extent, you can look at the minima of this energy function as being solution of the power flow equations, right? So in that sense, you have the situation where what you're seeing here in the image are the level sets of the energy function, and of course, at the minimum sees the solution of the power flow equation, kicked around by noise, and eventually, after a while, the system will exit the safe region, and at that point, you declare a failure, and that's the point where you drop that line. And our object is to estimate mathematically the statistical properties of x star, as well as trying to estimate the probability of reaching that point. That's going to be the main idea. So now, once you have a stochastic differential equation, you can, in principle, attack this issue with brute force, right? So which means that, well, you can actually, of course, simulate it. And this is a very classical method in stochastic differential equation for people who are familiar with it. Stochastic differential equations are a natural extension of integration of ordinary differential equations. So here I'm showing a method which is called the Milstein method. So the idea is actually quite simple. You actually decide on the characteristic time step, much like in the Euler method. You actually advance the system by delta t by adding the contribution of the drift term times delta t, and then the scaled version times the scaled version of the noise, right? So delta w is white noise. You sample it, and of course, because you have a limited horizon now, the noise is, then delta w is normal with mean zero and variance sigma squared. In this case, of course, I'm showing you just the scalar case, but there's a similar vector case. And then, of course, you check whether you've exceeded the threshold or not. And if you exceed the threshold, you declare a failure, and then you restart the simulation from the degrading network to actually try to simulate the cascade. So you could try to attack it with stochastic differential equation. That's one of the things we tried to do in the past. And of course, you run into challenges pretty quickly because it is, for actually getting good accuracy, you need very small delta t. You need very long horizon to observe failure. So these simulations take forever. So it is not a simple calculation to run. It is very expensive. It takes a lot to convince yourself you're converged, statistically speaking. So actually, this is very, very intensive. So as an alternative to that, we looked at an idea from analysis, which is called large deviation theory, which attempts to approximate the statistic of the exit time at small temperatures. That is for small tau in my case. Okay. I'll stop with this question. I'm not sure if the habit is to ask questions at the end or if we stop in the middle. Olivera, how should I do this?
Yeah, maybe we can leave the questions at the end. So
okay, I'll be happy to answer questions in the middle too. So this is like, just let me know if there's one. Probably the best way is, I'm sure you guys have handled them before. I don't mind stopping in the middle. I recognize this is stuff that sort of may not be familiar to a lot of people. So I don't mind stopping for clarification. So in any case, and let me know, just tell me and I'll be happy to stop. But continuing, so you could in principle now do cascade simulation by just running the stochastic differential equation, but that takes forever. So then, as I mentioned, we're going to do large deviation. So these are what I'm going to show you in the next slide are the fundamentals of the large deviation theory. This is called the Freidlin-Wentzell large deviation theory, and it goes like this. When you have a stochastic differential equation and on a subdomain D with the non-characteristic surface delta D, which means that the surface is not tangent to the flow lines, you have the following result, that the limit when tau goes to 0 of tau times the log of the expected time of the expected exit time, it's equal to the minimum over all x of a quantity which is called the quasi-potential, right? So this is an exact result, but of course it's a limit, but it's an exact result. And the quasi-potential is the minimum on, as I said, it's complicated. I don't mind the question if you guys have one. So the quasi-potential is the minimum of an energy function among all points which start at your x bar and end up at x, at which you minimize the following functional, which is phi dot minus b of phi times the variance, a version of the variance times phi dot minus b of phi. If you look carefully at this, this is nothing but a way to look at the what is the minimum residual to the stochastic differential equation that would get you to the point x, which is the exit point, right? So this is how V is defined. So fundamentally, to define a quasi-potential as a function of x, where x is any point in the domain, you actually compute a scaled version of the residual, which to the differential equation that you get you all the way to x, right? If you have no residual, you must stay at x bar, right? So you have no residual, you'll stay at x bar. You never escape the solution of the power flow equation, but of course the noise doesn't allow you to do that. So then there's going to be some trajectory which is going to get you to x bar. And the idea is that you're looking for the trajectory which has the minimum energy in this norm, because that is going to be the energy which will define the exit time. So that's the idea. And then among all the energies which are a function of x, you look at the exit points, at the points on the boundary which minimize this energy. And that value gives you the asymptotic of the exit time. If you look at it, once you have the value on the right, then you'll find out that the expected time is exponentially distributed as minus this value over tau, right? So this is so that's the idea. That's why you see the log here. So that's where you get fundamental exponential distribution. So this is a lot to process, But intuitively, one way to think about it is that you are penalizing you are actually looking for the minimum perturbation that would get you to the exit point. And that perturbation governs the exit time. So that's the idea. Okay, so this is actually why. So fields can be decomposed by transverse decompositions, which is a part which is gradient based and a part which is orthogonal to that. So you have that B has a gradient part and a part which is orthogonal to the gradient. And if you have such a decomposition, then you get the exit point. So whenever you are lucky enough to have such a transverse decomposition, you have that the quasi-potential V, which is, as you see, it's pretty ugly beast, can actually be decomposed as simply as the function of the energy function U. It's U at the point X minus U at the point X bar. So if you're lucky enough for the drift B to have this structure, then V can be computed much easily as a function only of a point U of X. And if you have U explicitly, then that quasi-potential is computable explicitly. Therefore, the statistics of the exit point is computable explicitly, right? So that's the idea. Okay, so then a bit of theory. So when you're in the quasi-stationary phase, when one it's less than t, it's less than the exponential of the minimum of this value of the difference in the quasi-potential scaled by the temperature tau. The temperature gives you the amount of noise you have in the system. A larger tau means more noise, a smaller tau means less noise. Then you have the derivative with respect to t of the probability of x times t. It's equal to minus lambda t, and lambda is called the exit rate, and g is called the probability current. And when you have the divergence of L is equal to 0, this current can be computed exactly, and it has the form which I'm going to show here. I'm going to go fast over this, but this is the upshot, and that's probably the only part which is at the end important for computation. It turns out that because of the work we spent in doing the structure for obtaining this energy function H, or I should say Chris DeMarco did to obtain this function H, then for this U, which is exactly the function H, and for the L, which is J times the gradient H of HY, we do have such a decomposition, and therefore we could actually, and therefore we can simplify the calculation by a lot in a way I'm going to explain here. So we're going to obtain the point X star, which minimizes this quasi-potential, which is fundamentally nothing else but the minimum of the energy function among all the points which satisfy the exit condition, which is the line energy limit condition, right? So if you look at the point, so if you look about what the solution of this problem is, it's nothing but a slightly perturbed version of the power flow, accounting for the smallest perturbation, which satisfies among the power flow equation, which will satisfy the exit condition, which is that the energy of your line reaches a certain point. So this is going to be the backbone of the calculation, trying to solve a slightly modified version of the power flow, which in some sense solves the smallest modification to the power flow equation, which would result in triggering the exit condition. So that is what ends up being the calculation. Once we have that point X star, we can actually compute analytically an approximation of the exit rate. The exit rate, again, it's 1 over the expected value of the exit time, right? So large rate means small time to exit, small rate means large time to exit. That is large time to failure, right? Large time to actually getting the line off. So then we end up with a not very pretty expression, mind you, but still computable, right? So if you have, remember, this is nothing but the gradient of this is nothing but approximately the right-hand side of the power flow equation. So this is computable. You have to compute the second derivative of this energy function. So you have to compute the Jacobian of the flow equations to compute this. And then all the other quantities are known once you solve the optimization problem. So it's ugly, but it's computable. And once you get the lambda, this tells you roughly 1 over the time to failure. And this is computable fundamentally by doing the power flow equations, a slightly modified version of this, as soon as you know the temperature, which is as soon as you know how much noise do you have in the system, right? So that is going to be the upshot, and this is going to be the core of the entire calculation. Okay, so then to summarize, this is what we're going to do to come up with the individual failure model, right? So this is what we call the zero order model. We're actually going to minimize the energy function, which I remind you, when you minimize it unconstrained, you get the power flow equation, right? And that's what you see here. If theta is less than theta max, then minimizing this energy function gives you just a solution of the power flow equations. And then we're gonna minimize it. We're gonna minimize this energy function subject to the exit constraint, subject to the triggering the line failure constraint. And again, this is now a slight modification of the power flow equations. And this X star then will allow us to compute the lambda, the failure rate. And then unfortunately, I forgot to say that once you have the failure rate, then you have that the exit time is approximately distributed as an exponential random variable with the parameter lambda. That is, the density is going to be e to the density of t is going to be e to the minus t over lambda, right? So this is that. Then you can actually simulate the exit time by once you have the lambda by just doing a simple sample from a stochastic random variable, which is very simple to simulate now. So that is the idea. So what we observe, we'll validate this model, with simulations, as you'll see in a moment. But what we observed is that it's useful to look at slightly higher perturbations and to correct this model at slightly higher temperature. A low temperature, the model is certainly correct, is probably so, but at higher temperature, the model may pose the problem. And the difficulty is that we can validate the model only at high temperature because the stochastic differential equation is very hard to run at low temperature. Fundamentally, the convergence is ridiculously slow. So because of that, we very much like to correct this at high temperature because that's the only place we can really validate it. So here we do a little bit of heuristic. The Freidlin-Wentzell theory is based on a perturbation argument. You can actually extend the perturbation argument as an expansion in tau. Tau is here the small parameters. So then the true probability of exit, it's actually a function of tau, and actually it's written like this, where fj of x are the functions which govern the expansion. So this is how the probability looks like. And I would consider, in my analysis, I consider only the zeroth order term, which is the first term, right? To correct for that, we also include the first term, which is tau times C1, right? So which is going to look like that. And here it's complicated because there's not a simple basis to compute the parameter C star, which actually now governs the calculation. We have done some analysis, and we have concluded that, and this is a heuristic, we observe that C1 can be approximately computed as C star C bar square root of tau over delta H. This is a heuristic. We've done, a lot of investigations, and we observed that this is almost always a good approximation of the first term, not the zero term of the first term. So to summarize, this is going to be our model of failure, right? The model of failure is going to be that we're going to compute C star, C bar, delta H, and all of them are computable based on running just the slightly modified power flow equation with that perturbation I mentioned at the beginning of the talk. Once we have that, I then have the distribution of the exit time as an exponential random variable with the parameter lambda. And that's going to be the calculation. Once that's true, I have a probabilistic model for the failure of each component, and I can put it together in kinetic Monte Carlo model. So that is the essence. Okay. Okay, so let's see how good it does. So far, this is all theory. So what I'm going to do, I'm going to compare simulations now, which means stochastic differential equation simulations with the analytical expression of the rate that I just computed, and try to see how well they do. So now we look at the exit time which is how fast we trigger the first line loss, as a function of tau. And you see here simulated the result with the blue curve, and you see here the analytical results with the yellow curve. And indeed, for the 3-bus system, as the theory predicted, when the temperature is low enough, the two match actually very well, right? So this is the first observation, which is indeed we validate our theory. A small temperature, we do observe that our theory, which has fundamentally just one power flow calculation, approximates the rate of escapes very well. So this is what you see here is the simulation of the probability of escape over many simulations, right? So this is the idea. Whereas in orange you see the analytical rate. We also validate the exponential distribution. So what you see here, like I said, we've run the model many times, and we counted how many times we get to the maximum energy tolerated by the line, and at the point we stop the simulation, and we look how much time it takes to do that. And again, if you look at the time and you plot the frequency in log scale, you do see that it does follow approximately a linear pattern, which is consistent with an exponential distribution with the rate lambda. And now what you see here is in orange, the simulated one, and what you see here in green is the computed one, again, with the one power flow calculation. So you do see that the match is pretty good, right? So certainly our theory seems to capture the failure rate reasonably well in this case. This is another validation, which is now we're looking about how so when you do a stochastic simulation, of course, the points at which you're going to exit, that means the points at which you're going to trigger the failure condition are going to be, of course, random variables. So of course, the question is that if X star, which is the point where you compute the minimum of the energy constrained by the failure condition, whether that approximates well the exit point, and it does, right? So here's the example. So what we have here is just on the angle variable θ2, because of course the exit point is in the multi-dimensional phase space, right? So it's a big point, but now we have just θ2, one of the angles, and you observe that the initial angle is here, the blue line, which means that the solution of the power flow equation of the unperturbed state, and then the exit time is indeed distributed as you see here as a Gaussian. It's actually the distribution is normal in the limit, a small temperature, as you can see, and indeed it's centered very well on X star, which is what the power flow solution of the power flow does compute. For the 30-bus system, the situation is not quite so nice, but we believe that has to do a lot with the fact that we're unable, as I mentioned before, to run a lot of simulations. so this is actually where we're running into trouble with the fact that the simulations are truly very slow compared to the analytical calculation. So what I'm showing you here, for the 30-bus system, I'm showing you here a number of things. I'm showing you so with with orange, I'm showing you the exit rate from the zeroth order model, the uncorrected model. With green, I'm showing you the first order correction computed analytically. Now with blue, with the dark blue, I'm showing you with the dark blue and the light blue, I'm showing you two simulation of the escape time, again as a function of temperature, and one of them with a delta t of 10 to the minus 6 and one of them with a delta t of 10 to the minus 5. And you see that as you reduce the time step, you do approach pretty well the first order correction. So it does look like that first order correction works pretty well. So certainly that is an improvement. It also tells you that delta t needs to be very small before you see the agreement. So indeed, trying to validate that is difficult, but we do believe that our theory is correct for the reasons I just mentioned. A few words about the distribution. So this is just about the expected failure times. So the expected failure times match well. Does the distribution match that well? Here, not as well as we'd like it to do. Now, again, what I'm showing you here is, again, the distribution of the exit times with the density log scale, right? So a perfect exponential variable. So certainly the distribution is exponential. and the empirical rate is this. The empirical rate is this orange line, whereas our theory predicts this green and this green and this lambda 0, which is the zero order correction, is the green one, whereas lambda 1, the first order correction, is the red one. And there is some discrepancy, and we believe it's primarily because we cannot afford to simulate it to the point where we converge the simulation. So we do believe that's what it is. But of course, it's a belief, it's not a proof. But then again, how would you prove it, right? So this is that's fundamentally the issue. So I'm gonna, because I'm running close on the limit of time, now that I have the system, I mean, I have other validations. I can return to them if there's questions. So we are ready to compute a aggregate line failure model. So it's actually kind of simple, right? So we actually we simulate the cascade by jumping between line failures with the probability given by the individual failure rate. This is called a kinetic Monte Carlo model. And so, you know, so this is how it works. We initialize the sequence of failures. We compute X bar, which is the power flow solution for a given configuration, which either if it's the initial or it's the degraded one. So you start with the power flow calculation, right? Then you compute the constrained power flow calculation for each of the lines which are still left, right? Then you compute the aggregate, the aggregate rate, and then you sample the failure, and then you sample the failure time from an exponential distribution with the rate lambda that we defined, and then we sample the fail line lambda star with probability lambda L star over lambda S to S hat, and of course, the larger the probability, the more likely is the line the more likely is that line to be picked. But because this is stochastic, you don't necessarily always pick the line which has the highest rate, which is natural because again, there is some randomness in the system. So you pick that rate only on average, but not on any one simulation. And then once you do that, you remove the line and you restart the calculation. And then you keep doing this until the end of the cascade. So that's the model, right? So this is sort of like, you know, a small sketch of how the model looks like. You start with the line undegraded, then you can simulate to, you know, losing line 1, 2, 3, or 4. From here, you can simulate losing any of the 2 lines, then any of the 3 lines until you end up with a full cascade, right? So this is to the full blackout, I should mean, not a full cascade. Okay, so now some empirical validation, right? So this is so here we benefit from data from our colleague Ian Dobson, who actually works with us on this project, but though not on this particular model. Where actually one of the statistics that he's collected, and I believe this is based on the BPA data. One of the statistics you can try to collect and try to match is called what he calls the SEPSI, which is that you actually take the BPA data, process it, organize it in generations, meaning that if 2 successive failures occur within 1 minute, you declare them they're part of the same generation, and then you count how many generations are in a cascade. And then you process all the data, all the failure data, and then you plot it as a function of the number of generations. So you plot the number of occurrences of a generation of a certain size versus the number of generation. And it's understood that if you do this in log-log plot, you should obtain a line which is called Zipf's law. And Professor Dobson has spent much of his life looking at this, and he noted that the Zipf line should end up having a slope of about 3. Right, so this is it actually varies. It's like 2.8 in summer and 3.3 in winter, but it's roughly about 3. Right, so this is the empirical evidence we have, and we observe with some satisfaction that indeed our simulator does capture roughly a very similar Zipf law, where actually you get that. So we, of course, we cannot afford to have that many generations. Because even when you do the KMC model and you collect it, and remember the cost of now failing a line is just to solve a power flow and then, you know, solving as many power flows as lines in the system and you know, tossing a coin. It still takes a lot to do that. It's a heck of a lot less compared the stochastic simulator, but it's still a lot. So we're able to obtain only 9 or 10 generations, right? So this is but certainly when you look at the 9 or 10 generations, you do observe that the empirical proportion does match reasonably well Zipf's law with the factor of about 3.27, which is certainly very close to 3. So it does, and again, I should say this was done for the 118 bus system. So it's actually even plausible that for larger system, we're going to get even closer to 3, actually. But so that's the model, right? So the model is, in that sense, we believe predictive. I mean, assuming that all failures are initiated by noise, the model is predictive. Of course, that's not true, as we know. But in a world where the failure is initiated by the noise in the system, then this appears to be a reasonable model, and it matches reasonably well the data that we do have about cascades. So I have just 5 minutes left, and I would rather stop and take questions. I'll just very quickly explain that we have thought about losses too, and it's not too bad. But I'll answer these questions if I'll go to this if there's interest. And then also we thought about how to use this in decision, and we have ideas here too, whereby we try to solve optimization problems based just on the constraint of the rate of the first exit, and it does seem to control the subsequent exits reasonable well, the subsequent failures reasonable well, in the sense that if you reduce the rate of the first exit, you do reduce the rate of the subsequent exits as well. So you can use that as a proxy for minimizing cascade probability. But with that said, I'll stop here to allow time for a few questions.
Okay, thank you so much, Dr. Mihai Anitescu, for your presentation. This was very helpful. There was a lot of very important things that you mentioned. Does anyone has any question to ask? You can text the questions if you want in the chat, and I will read them in case if you don't want to ask them by yourself verbally. Well, I have one question I can ask. Have you found some parts of the simulation that can be replaced with a surrogate model based on machine learning to reduce the computational cost?
So it's plausible, but then remember, you need the data to run the machine learning on, and the simulations are extremely expensive, right? So this is how can you generate the data is the problem, right? So that is the most limiting factor, right? So even if you take the stochastic differential equation to be your first principles model, then running that is extremely difficult at low temperature. So that's the difficulty. Sure, but where are you going to get the data? That's the problem.
Yeah, the data. Data is always a problem.
I mean, data is not a problem. The lack of data is a problem, right? So this is
Yeah. Okay, someone else? Does someone else has a question?
Hey, Mihai, this is Henry. Thank you again for this wonderful talk. A lot of details, and I was trying hard to follow all the equations.
Sorry about that, but
no, it's good. It's good. Every time I listen, learn more about your work. One quick question. Maybe I missed the details when you were presenting. So how can this formulation be expanded to a very large scale power system?
I mean, actually, I don't have the data here, but we've been running it on the PEGAS 10,000, right? So, as long as you can compute a power flow on that system, you can compute the exit rate, right? So that's doable, right? The issue is, of course, that the number of failure is combinatorial, right? So, yeah. So we can do it. The issue is that, of course, for a large system, you have to screen. You cannot possibly afford, right? We cannot possibly afford to compute all the possible failure rates for a large system. So then we have to start screening them somehow. And here probably, the experience a lot of people have in screening contingencies may come, of course, very helpful, right? So I'm thinking that probably the way we're going to do this is actually look at the logic that people used to screen contingencies before and try to use the same logic to try to look at the only rates we compute. if we can reduce the rates to say about like, if we can get it to a point where we compute just say 10 rates per generation, it's not a problem. It's something we could compute tomorrow, and we already do. Like computing the rate for the 10,000, it's like I said, it takes the same it would take the power flow, so it's not expensive by itself. It is the fact that you cannot afford to compute too many in a generation. But here, like I think that's probably the best answer I have. It's early times for large networks, but probably marrying this with the way people have done continuous screening before, we can probably do that.
Great, thank you, Mihai.
Does anyone else has a question?
If Oliver, if no one else, let me ask another question. Since I know Mihai's work pretty well, I guess. So this question may not be exactly about this talk, but more about maybe a broader view. So Mihai, I know you've been working on resilience metrics for a while.
Right.
So how does this cascading failure method you talk about either tie or not tie to the resilience?
You're right. This is it.
Sorry, since I know you, and so the question kind of go beyond what you're talking about today.
No, you're absolutely right. So probably you would be able to show, right? I didn't get that far, right? So this is but our intent, and this is where we got here, right? So our intent, I mean, of course, for resilience, you have to model the restoration process, right? So this is, I mean, to really talk about resilience, you have to talk about. So this certainly does very well to talk about the robustness, right? Because this explains, how you control the system not to fall very far, right? But it's not just resilience. But fundamentally, we do believe that we can show that solving the security constraint power flow problem, but where you use the probabilistic, the rates obtained by this calculation will get you pretty close to get a metric which is close to the resilience metric, fundamentally. That's what I think is gonna. So my thinking right now is to do n-1 plus the second failure being probabilistic given by this model. And I believe that would be a pretty good proxy. Surely that gives you only how far the system fails. But I do believe that that's gonna correlate well with how fast you can get it out of something, which is what resilience ought to be. So that's our thinking right now, but it's early times for optimization, right? So this is we're like, we just did a very small calculation or something, but we do expect that that's doable.
Okay, excellent.
But this is actually one missing piece here is we have to model humans intervening and fixing, which we don't do. Right. So if you really want to talk about resilience, you should not model only a failure model, but you should also model a restoration model, and that's actually doable. But then, of course, the restoration model is not physics based, right? It's based on the operator availability. So that requires more input from the technical side. That's not a purely mathematical endeavor, certainly. But the other way to do it is actually to model the restoration process explicitly and try to understand. Indeed, right. Then you would simulate both failures and restorations, and you would have everything you need to come up with the resilience metric.
Right.
Right. We have a question in our chat. Can you see Mihai, or I can read it?
So okay. So can we get access to the slides? Right. If you encounter contingency scenarios for which solving the power flow is particularly challenging, yes. I mean, so fundamentally, and this is something in the issues here. You're right. So eventually, once you start to pull lines off, eventually you don't find solutions to the power flow equation anymore. Once in a while, so we do. Right. So what we do here is that we. I mean, two things. First of all, and I didn't specify that, when the voltage, right? So we solve if you solve the power flow equation and the voltage at a load node is too small, we have to remove that node because you trigger another condition, right? So that's removed. So that actually gives you a better chance once you remove the load node that you're going to get feasibility. So that improves that. So that's one thing. And certainly there's issues with the topology, right? So eventually get things that you cannot get feasibility topology, which we remove as well. I don't remember running into a problem that when we did that, we couldn't solve it. But then again, the person who did the actual calculation is not here, and I'm not that person. But there is a bit of post-processing, which does improve the odds of not running into trouble, and also models the reality, right? You're not going to allow a load node with a low voltage to stay in, because you can't, right? So this is you have to remove that. I hope I answered your question. I mean, one of the advantages, it's actually, so there's actually a really subtle advantage here. And actually, Joseph, I'm really happy you asked this question. And this is something which I'm a numerical optimizer. That's sort of like, 60% of my business, right? So the interesting fact in this approach to power flow, the energy approach to the power flow, is that you'll always find a solution. Right, and the reason for that, has to do with the fact that that's actually pretty nifty. And again, it's the contribution of Chris DeMarco, not ours, right? So this comes from the. Let me try to. Okay, here, right? So just a second. I want the one with 3 bars. This one, right? So fundamentally, because any minimum of Chris DeMarco's energy function is the solution of the power flow equation. All I have to do is to find the minimum of this function, and that minimum will always exist, irrespective of how degraded the conformation is. So you're not in the situation where you sort the power flow equation as a linear equation where Newton may not converge and you don't know what to do. A minimum of H, you can show that H is bounded below. A minimum of H will always exist, right? So that's actually the interesting situation where you formulate the power flow in minimization form. You're guaranteed to always find a solution. So that's actually a really big plus of a minimization formulation. Of course, that works only for the lossless case. In the lossy case, that's not true, right? So that is the problem. So this is true only for the lossless case.
Okay, thank you so much. Joseph says thank you as well. Well, if no one else has a question, I think with this we can conclude the webinar. Dr. Anitescu, thank you so much for finding your time to be part of our webinar series and sharing your experience with our community. Or just another reminder for the attendees that they can find the video on our website. And
it's my pleasure, actually, because somebody asked for the slides. So the slides are a bit improvised, but this is all part of a document which is on archive, and I'll send you the link to it. This is all public, so I'll just send you I mean, like 90% of this is public. So I'll just send you that preprint. It certainly has everything I talked about. So, okay, thank you very much for the invitation. Thank you for the interest. It was my pleasure, and good luck. And I hope to myself be present to other meetings of yours.
Yes, thank you. Maybe before we leave, I just want to call Henry if he has something to say in the end before we go.
Not really. I just add my thank you to Mihai and also yourself, Oliver, for organizing. Also to the audience for joining us today.
Yes, thank you. Yes, thank you both of you very much. Have a great rest of the day.
Thank you much, Oliver. You too, and the same to all the members of the committee. Thank you, guys. Bye-bye.
Yeah, thank you. Bye.
Bye. Thank you, Mihai.
Bye.